Welcome in my lab. I'm really happy to be there with you for this The Thing virtual conference. My name is Paul. I'm also known as a Disk91, so disk91.com. I'm a blogger, I'm a IoT addict, I'm a developer. I'm in a lot of different things around the IoT domain. And one of the particular things I want to share with you today for the next 30 minutes it's an SDK, a software development kit I'm developing since about a year, and this software development kit is really specialized in working on IoT domain with LP1 like LoRaWan, but also Sigfox, and it will help you to really quickly make a prototype for your IoT, but not only a prototype. The objective of this SDK is to go in production with it. So you have in it all what you need for securing your IoT, to debug your IoT, and so on. So now let's go for 30 minutes of code all together. For this workshop, we are going to use a card coming from ST Microelectronics, and this board is a LR1 board. It has inside a module. This module is a Murata ABZ module. This module is basically a STM32L0 MCU, so really a good MCU for IoT, low power and so on. And inside this module you also have a Semtech 1276 transceiver, so it means that you can do LoRaWan or you can do Sigfox with a such board. This is really why I really like this board in this module, because it's not an expensive module and you can access all the major LP1 in a single module, so that's really interesting. The SDK we are going to review works really well on this module because it's the one I mostly use, but it also works on different STM32, or eventually it's easy to port it to different MCUs. So IT-SDK is an open source project. You can find it on GitHub, and on my GitHub page you will find all the information about the SDK with all the data that is currently supported. This is really evolving quickly, so there's a lot of many things there. So the idea is to have a generic SDK because I made a lot of IoT devices, and my problem is when the platform is changing, I have to adapt all my code and so on. So IT-SDK is an abstraction layer, so it's between a HAL and between a user application, and so you have a layer with the hardware implementation. Here it's a STM32 layer, and on top of this you have a generic abstract layer including I2C SPI to allow also to have drivers to be generic, and you also have all the communication stacks like Sigfox and LoRaWan, but a lot of other tools that are really useful. So the web page of the project is describing all that stuff. You have a certain number of sensors that are already implemented in the SDK. I'm working to improve this, and other users that are implementing the SDK also add some projects, so that's good. So to get started, we configure the project, we initiate the program with CubeMX. CubeMX is a tool provided by ST Micro to configure the MCU. And here we are working on a board, so the LR1 board. So it's really easy to initialize the project searching this board from CubeMX. So we're gonna get it, selected it, and it's going to be initialized with what we need, because in fact the Murata is a module, so you have the MCU and you have other peripheral around, so it's important to have the pre-configuration. You save time from starting from scratch. So for the SDK, it's good to have a watchdog. I really like watchdog to securize what we do, and the SDK we have a setting with a prescaler divided by 256 that's allowed to have a long period of watchdog if we want. So that's the default settings. Then we need the RTC. The RTC is important because it's one that is wake up the system when we are in low power mode on a regular basis. So we use that RTC, and it's also a time reference. As on this device, we have the RTC that can be connected to an external crystal, which is more precise than the internal oscillator. So that's interesting to use the RTC also for this, as we need precise timing for communication to get the right timing for reception windows and things like this on LoRa. Okay, so the RTC is configured with a specific asynchronous and synchronous pre-divider. The objective is to have a earth rate of 1 millisecond for the RTC to be efficient. We ensure that we have the interrupt setting to wake up through the RTC system. Then we can activate ADC to get temperature and VCC information also from the chip, which is something that could be useful in your design. And then we have some last setup. We can check just GPIO, ensuring that they are enabled, the interrupt and GPIO are enabled, but this is a default setting, so no problem with this. I'm going to activate UART, the USART number 2, and set up it at 9600 bits per second, which is the maximum rate we can have to wake up the system and catch the transmission. For Disk91, this timer is used to synchronize. To synchronize the C-stick on the RTC. Okay, and for the RTC, we're gonna activate the external crystal. So it means that on a clock configuration, we are routing RTC on LSC, and we also need to route the UART to HSI 16. Otherwise, we cannot wake up the device from the UART 2 if we are on NP clock 1. So the setup is done now. We can create a project. So we're gonna give a name to that project. So it's ttn-conf. We can go to advanced application structure, and the main important thing is to select the target for the compilation. And I'm selecting KubeIDE, sorry. It's the development environment that STA has recently provided. It's Eclipse-based, GCC-based environment, so open source like this. We have some extra settings for the project, as you have seen. And once we have done that, we can generate the code. So this is basically building the code structure, and we are going to be able to open this code structure in Eclipse environment. So it's KubeIDE. So it's starting. It's quite fast, but it's good. Now we have our project, and on our project, what we need to do now is to add the SDK inside our project repository. For this, I would like to have something where we separate the generated code from the CubeMX and our project. So everything goes in a separate repository. So we just have to clone the SDK into the CubeMX generated project. So to get that, we just need, in fact, to clone, getting the clone URL from GitHub. So we get it, we git clone with the selected URL, and yeah, we get everything. So that's quite fast. We have it. So now in our project structure, we see that we have now STM32 IT-SDK directory where we have the SDK. So we have a directory with some documentation, the ink and the source directories. And now we need to make the link between our project and there's directories we have added. So at first we need to indicate that we have a new source we want to compile. So for this we go to C++ general, then in patch ensemble, and we search for our directory. in source location. Be careful in the configuration. You have to select the release configuration and normally also the debug configuration. Otherwise, you have half your setting done. And for the header, so we go in build settings, in tool settings, and then in the include, and we add the include path. So it's quite already configured because I already did it on previous project. Okay, and he asked to rebuild, but we are not yet ready for the rebuild. There is one last thing in the configuration, which is quite cool. We add a pre-build step, and this pre-build step will just touch one file, and this file is able to modify the date of the build, and so from the console on the device you will be able to see what was the build. So that's something really useful when you are making a lot of build and sometimes you don't know what build was it in your device. So you have this feature, which is really easy to use. So now we are going to create a skeleton for a project. So we have templates. So we take the template, the project underscore main, one we want. Here I take the LoRaWan, and we copy it in the CubeMX project structure. So that way we touch not a lot of things in the project generated. So basically it's something really classical. You have a project setup, so it starts once at boot, and then you have a project loop, and on this loop you would have things that will be repeated many times. Okay, and this place, the project main, is where you start your code. Okay, everything goes there for what you do. Basically, you modify not a lot of things. But we need to have project setup and project loop to be called by the system. So we need to modify the main file that has been generated by CubeMX. And on this main file, we need to call a setup and we need to call a main. So for this, we have two includes. So you see that we include we add the includes in a part of the code which is reserved for user. So it means that if we regenerate the project structure from CubeMX, this won't have to be done again. It will stay there. So now we call a setup, but you see it's not project setup, it's IT-SDK setup. So the same thing, we do it at this port after the CubeMX init, and in a place where it will be kept when we regenerate the project. And then we got a loop. Once again, it's not a project loop, but IT-SDK loop. And just be careful because the place we put it is not really user-friendly, in fact. So you see we have the main that is started when we fire up the MCU. This main is calling IT-SDK setup and IT-SDK loop. And now we have our code in project setup and project loop. So to make the link, we have a main file which is inside the IT-SDK, and this main file does the internal SDK setup and loop. So you see that it is initializing the different components and it calls the project setup. You see that there is a lot of dsdefine or dsif. It's because the SDK has been made with a lot of possibility of inclusion or exclusion of module. This helps to run the project even on really small memory targets. So we can deactivate a lot of module. So now you see that the IT-SDK is calling the project part, and so we have our setup. In that setup, we are initializing joining LoRaWan and then firing a message. Okay, and you saw that we have a file which is IT-SDK config, and this file is really important because it's that file that defines all the configuration, all the module we want to activate or not activate, and so on. So it's really the file we are focusing on for the configuration. So like for the project, we have a skeleton. We need to create a folder, an IT-SDK folder. In that one, we are going to copy the config file. So we have a template in inc IT-SDK config.h.template. So we make a copy into our project structure, rename it to remove the template extension. Okay, and inside this file, we're gonna find all the different settings to get started. So we have some information like the version of the SDK and also the version of the application you are developing. Okay, you can put it at this point. We are defining the platform, so basically in the future, in the coming future, we will be able having something like Nordic, for example, target, and we can just change it at this point and everything is recompiled and working on this other target. We have sub-target for different device we have. We have information about the target itself, size, and so on. We are indicating the different serial communication we want. We can activate or not the RTC. We have a frequency for the RTC. And we can identify what is the best source for the clock, is that the RTC or the internal RC, and both will be aligned on the best. Okay, we can activate different I2C, SPI, and so on. And we have the logger. So the logger, we can select if we want to have a, debug, info, warning, error things, which is the F here, or selecting any certain level, and we can either select also different output for this log. It can be on multiple serial or things like this. We have internal logs we can activate or deactivate. If we don't need them, deactivate it will save space. Okay, and we have an internal system with an error report that allow to have some logs that stay inside the memory in the EPROM. And so if you have a device on a field, I don't know, rebooting for example, and you want to understand why, you can check that log days after by checking this error memory. The system is basically working low power, so you have not to do a lot of things to go low power. It's built by default, but you need to select what kind of wake up you want to have. So here as an example, we want to wake up on UART2, which is important because it's a serial console we are going to use. And we have a regular wake up with the RTC, so here we can decide of the period. So we have one alpha second there, so that's good for test, but it can be 2 or 3 seconds as you want. When we are in deep sleep, we can select the different model we want to stop. So we don't need the ADC, we don't need the timer, we don't need the SPI, so we can shut them down. And after you have a long configuration, I won't do there because it's a bit long, but for each of the GPIO, you can decide the GPIO you want to switch to analog or the one you want to keep configured as they are. So it depends on what you do, and you have to think about a bit about this. This is saving power basically. So here I keep all configured on when sleeping. So after we have some internal thing like a task and a scheduler that can be used. We have a configuration stored in EEPROM. So we have one for the SDK, but we can add one for the application, so we can enable that part. It will be simple to manage. And we have something which is really important. We are doing communication, and by doing communication, it means that we have keys. Like we have the app key, we have the communication keys for Sigfox, for LoRa. They are really important, and we really need to protect them. So here we have a secure store. It's not a perfect solution, it's not a secure element, but inside the EEPROM, the keys are stored encrypted in AES. The key of the store is also encrypted and protected by a key, and the key is generated through an algorithm. So it means that if you want to get the key out of the device, you need to deassemble and understand the algorithm of key generation to get the basic key, and then to reverse the AES encryption. So nothing is impossible, but it's a bit complex, and so that's quite good protection. We have a console. So the console is have a public part and a private part. So I mean, your user can check the console and get some information, but if you want to administrate the device, you log to the console, and so for this you have a password. There it's change me, but you can change it, and you can change it for any device. So I mean, here we are setting some default values. The keys you see there, they are default keys for your prototype basically. But once you are in production, you can change all of this for every of your device, and not by recompiling, but just by using the console. So that's interesting. Now we activate the communication layer. So here we are doing LoRaWan. So I enable the LoRaWan library. And basically, that's the main thing I have to do. In the SDK, I also add some encryption layer on top of the LoRaWan encryption system. So it's end-to-end encryption on the payload. You have a spec protocol, and you have also AES. So you can select one, two, or both. Okay, you do as you want. And for this, once again, you have some default keys that are set up here, and for sure it's better to change them, and you will be able to change them for every device also in your production cycle. Okay, so you can have you can add a lot of security on this. By enabling the LoRaWan lib, you see that I need another config file. So the configuration for the LoRaWan is separated in a second file, so we can get the template as we did previously for config, and so we copy it, we rename it. And this file has been made for the Murata chip, so most of the configuration is by default good, but you can tweak a bit, and basically if you have any Semtex 1276, it can work, or we can quickly change the future for 62 and so on. So you have a couple of settings there. You select the channel you want to, the zone you want to support, and then we need to get the credential for this device. So for this, I've switched to the sync console. I've created an application for this purpose, and now I will register a new device. So can select any device ID, and the platform is going to generate the device UI, the app key, and app UI. So I have all those elements, and to set up the SDK, it's really easy. You see that we can get the C style initializer, so we can just copy and paste it to the config file. So here we have a dev UI. Okay, you see on top of this there is the different regions that are allowed. You can comment some of them if you want to reduce the memory footprint. So we do this for the application UI also, and then we are going to do this also for the app key. So once again, what we are setting here is a default configuration. It's really useful for a prototype, because for a prototype we want to compile and fire it, and we want it to run it. But in production, all of this will be easy to change through an industrial process. So you can put default values there, and automatically then you can change that later. So that's an important point that you need to notice. So the last things is, we can enable the second layer of encryption. That's also for optimizing the footprint of the code. You can inactivate if you don't use it. Otherwise, for every frame you send, you can select to enable or disable it, so the code is there. There is other setting on the bottom for the chip with the different GPIOs that I configured. So it's by default we have the right values for a Murata device, but if you use AF95 for example, you will have to change a bit the settings. Now we can compile it, and yeah, you see that we have spent about 20 minutes from scratch, and we have something that is ready to transmit communication over LoRaWan with a Murata chip. Okay, that's my point of view. That's quite good. So the board is good. There is a USB transmission, so you can upload through USB your code. You see that the board is blinking, and so we are receiving the firmware. On the window, on the right part, you have the console connected to USB on UART2. So you see that we are joining TTN. Oh, cool! We have the status that's changed, so the connection has been seen, and now we are joined, and we can send the first message. So we see the frame there, and we can also take a look to the data. So we got the payload 0, 1, 2, 3, and so on. So cool! It works! That's good. I'm happy. Yeah, it's like a demo effect. But it works. Cool. The pleasure of something which is not indirect. So let's see the console. I tell you that there is a console, which is interesting. That you see you can pass some command. You have a help, and you can see a version where you have the build and the build time. Right now I've been connected as a private console, typing the change me password. So I have more options on this console. I can do things like checking the battery level, for example. Yeah, so cool. Battery level is good. We have different information like taking a look to the historical logs. I tell you that we have in the EEPROM a storage of the past error. So here you see that there is information, warning log, and I can check the error code and see what happened. It's a reboot, the reason of reboot, and things like this. And you can add your own for sure. On the secure store, you see that here we can set up all the LoRaWan or Sigfox configuration. So in an industrial process, you just have to connect a serial line and have a program to automatically pass these different commands. You see that we can, from this console, see and change some of the parameter, and there is some parameter we can change. So the keys, for example, you cannot get the keys from the console. It's a security. So here I see this device ID. You can get it from the console. Okay. In terms of configuration, we have a configuration and a shadow configuration. So this is the configuration of the device out of the LoRaWan parameters, and so we can change the configuration of the different device and commit at the end. It's to ensure that we don't have an unsafe configuration by doing it step by step. So that's something that can be useful also. And all the parameters of LoRaWan are part of this configuration. So this works through the console, but you can also use all these features by a downlink, for example, to make configuration from downlink. Okay, so now you've seen most of what we can do with the SDK in 25 minutes. And I mean, any IoT project is always starting by LED blinking. Okay, I prefer to start an IoT project by communicating. For me, it makes more sense, but we need to conclude with LED blinking. So let's blink a LED. So we have this GPIO interface in an abstraction layer for GPIO. So we are going to configure a GPIO. We have a bank and GPIO number, quite generic. And then we say it's output. Push-pull. So I reset this GPIO to set it to 0, basically. And now we want to blink it twice a second. So I'm going to create a task. Okay, and this task will be called 2 times per second. So it's the scheduler module. So I register a new SCAD running every 500 milliseconds. And I fire the first event of this task immediately, so right after the registration. And I associate to the task a function we are going to define. So it's a function named task. So now we define the task function. So it's simple void task void, basically. And inside this task, we are going to do 2 things. The first one is to toggle the LED, so toggle the GPIO through the generic interface. And then we are going just to print something with a log. So it's a log.info, so it's a FO level. Just make a a period, and we're good. Okay, so we have everything for making this LED blinking up. That's a direct impact, doing some mistake in typing. Okay, so now that's solved. We have our code generated. We send it to the device. So the transfer is in progress. We see that on the LED, which is blinking. And what happened? Oh, we are booting. We are joining TTN. You remember the task is after firing the first message. Yeah, it's blinking, but that's not a LED. I mean, that's just a point of light. Oh, okay. Now we have real IoT with a real LED blinking. Yeah, that's cool. So I hope that you've had a really great time with me discovering this SDK, and hope that you will be happy to use it, contribute to it. So let's stay in contact. See you soon, and don't forget to follow my blog disk91.com. Have a good conference and stay home.